Hi guys, welcome back to AP Statistics. This is Mr. Robeson. Today we are going to start looking at sampling distributions. All right, so we got to go over what the difference between samples and populations here first, so a little bit of review. So remember, we have a population, and from a population is everybody that we could possibly want to sample or want to know about in whatever study we're doing. The sample is just a small part of that population that we're going to actually take and like ask questions or use for our experiment. That's our sample. So we take our sample and we collect data from our sample. So we take our sample, we follow this arrow here, and we start collecting data from the sample. We get from that sample some sort of information, like we get a sample mean, say, X bar, or we get a certain proportion of people that say yes to some sort of thing, or we get a sample standard deviation, or something like that. And from that information, we infer about the population. So once we get this information, we use it to take a best guess about what the population mean is, or the population proportion, or the population standard deviation, and so on. This is called statistical inference. This was our fourth domain. At the very beginning of the school year, we went over 4 different domains of statistics. The fourth domain was statistical inference, and that's really what we're going to focus on this semester. All right. So remember, every time we take a different random sample, we're going to get different statistics. So like one mean will not exactly match the other mean, like from a different sample. They will be slightly different. Like hopefully they'll be close to whatever the true mean is. Remember, the true mean for the population is mu. Right, hopefully they'll be close to that. So what we're going to start talking about here is what's called a sampling distribution. That's all possible statistics. So we take all possible samples, we find all possible sample means, and we compare them. That's our sampling distribution. All right, so recall, a parameter is some sort of characteristic of a population. P goes with P, population parameter, and a statistic is some sort of number or characteristic that goes with the sample. Remember, we had SS, sample statistic. All right, so population symbols, population parameters, we use mu, mu. Right, that's how we say that. It's a Greek letter. Or we have mu sub x, where x was ever our variable. That's fine too. We can put an x, we can put little words down there. That's fine. Same with standard deviation, sigma sub x. And now we're introducing proportion, which is basically like a probability of something happen, like the probability of someone saying yes to this, the probability of someone being in favor of some sort of resolution or against it. It's just a proportion. It's usually written as a decimal. We'll look at some of those here later. All right, remember when we take samples, we have X bar. That's how we say that, X and then bar. All right, it's the sample mean. We have sample standard deviation, which is lowercase s or lowercase s with an X. And we have P with this on it. It means P hat. It is not the same thing as Y hat and X hat. It is not predicted. Well, I guess it is kind of predicted because it is a sample. But yeah, it's sample information. All right, so usually this time of year, we do everything with experiments. But since we are virtual this year, I'll just have to show you some results. So we took pennies. So I brought in thousands of pennies. I believe we counted once and it was close to 2,000 pennies, or in a giant tub in my classroom somewhere in the closet. All right, and we had 100 different students just take one penny at a time and record its date. So there's a date on each of the pennies, and this is what we ended up with. Notice this is pretty much skewed left. All right, we got a tiny little bit over here. We got it bumps down, it goes up. There's our median there, I guess, or our mode there. And if I actually went through this data, the mean for this data was right around here. It was right around 1999. What a great year, the year I graduated high school. Right, so that was our mean from this sample of 100 pennies. All right, next, what I had people do is, and I had fewer people, it was a little more work this time. So fewer people did this, but we had 75 samples of size 5. So our N here is 5, and we have 75 total samples. So this is our sample size, and this is the number of samples. Those are 2 different things, all right? Each dot is the mean of a sample of 5. So each one of these dots has a little X bar on it. And you can't really see it, but each one does have an X bar on it. And those are means. Now notice it's not quite as spread out. So the spread has decreased. And we're getting more symmetrical about the mean. Like, sure, there's a little bit of a bump right here still, but we're getting more of kind of like an even hump. Not perfect yet, but right here the mean was still 1999. Weird. All right, and then we had 20 or 75 samples. I think it was 75 of size 20. So this was our sample size here is 20, and we took 75 of those samples. So I had 75 people go up, grab 20 pennies out of the bin, find the mean of each of those samples, and then they put a dot up here. And now look at our distribution. Like, it's not perfect, but it's looking closer and closer to a normal distribution. It's not quite there yet, but it's looking closer. And notice the mean is still, the mean for this distribution of all these samples is still right around 1999. So the mean seems to stay the same for all of them, but they get less spread out. So the standard deviation for each of these distributions is decreasing as n is increasing. All right, so that's important. The mean is going to stay the same. Right? And even though it was very skewed to start, it's becoming, it's even kind of skewed the opposite direction here, but it's becoming more and more like a normal distribution here. All right, what about with proportions? So I have 100 blue marbles, 100 red marbles. And we take samples of size 20. Simple random samples. All right, right now it's half and half. So if we look at, say, the proportion where P equals the proportion that are red, say. All right, so if we took 1, 2, 3 samples here, this one had 8 red out of 20, so our P hat here would be 0.4. This one had 11 red out of 20, so this P hat would be 0.55. This one had 13. I mean, it's getting a little high, but it's still, it seems reasonable to me, 0.65. And if we take all of these P hats and we put them together, this is what the distribution ends up looking like. Neato, huh? So right in the middle here is still our original P. So the mean of all the P hats is still equal to P, it looks like. All right, so the population distribution gives values of the variable for all individual, so that's the population. All right, distribution of sample data. So this is the sampling distribution here, because this is a distribution of all the sample data is here. All right, so we have the population distribution. We have the distribution of each sample. So this would be like one distribution. This would be one distribution. And then this would be one distribution. So we really have 3 distinct distributions happening. The population, each individual sample is a distribution. And then we have the sampling. This ing at the end makes all the difference. Sampling distribution. It is the distribution of all the possible sample statistics. All right, so notation I've kind of been using already. If we want the mean of the sampling distribution, it's a mu with a little sub x bar. The standard deviation of the sampling distribution is the standard deviation with a sub x bar. Mean of a sampling distribution if we're working with a portion is a mean sub p hat. And the standard deviation is the sigma sub p hat if we're working with p's. All right, hopefully these are found using what we call unbiased estimators. It's a statistic used to estimate the parameter. In other words, it's a sample statistic. All right, it's the mean of its sampling distribution is equal to the true value of the parameter being estimated. So in other words, we're saying the mean of the sampling distribution should be equal to the actual mean. The mean of the sampling distribution for a proportion should be equal to the true proportion from the population, the parameter. That's what happens if we get unbiased estimators. All right. The variability, though, is not going to be the same. In fact, larger samples give smaller spread. So this should be much less than the standard deviation for the actual population. Same with this, should be much less than the standard deviation for the actual population. All right, the bigger our sample size, the smaller the spread gets. All right, so that's important. All right, and this works as long as the population is at least 10 times larger than the sample. If the samples get to be too big, then it doesn't really work because all of our samples are not independent anymore, and we need them to be independent of each other. All right, getting near the end here. So this is, again, just the introduction. So we got 2 more things we should talk about, and that's variability and bias when we are finding our samples. So remember, bias is some sort of systematic factor in our experiment that leads to a systematic difference. So like we want to hit the bullseye. That's what we're aiming for, is the bullseye here. But we end up with all of our darts hitting up here, way far away from the bullseye. So this has high bias because all of our answers are way far away from where we would think they would be. But the variability is low because they're close together. They're not very spread out. So variability means how spread out they are. So if we look at this one here, now, this one actually probably wouldn't be too bad. This is higher variability, but the bias isn't bad because they're all centered around the bullseye. All right, so this one is probably our worst thing right here. So if we have a lot of bias, we're way off from the bullseye. And they're very spread out. They're still all over the place. Big circle around here. All right, so this is high bias and high variability. That's not getting us a good estimate. This is a very bad estimate. All right, this one is also a bad estimate, but it's some sort of systematic thing that we could probably fix. This one's probably getting us a good estimate. This one is a great estimate. So this one, all of our samples are getting right here where we think the actual answer is. And they're not super spread out. They're all close. So we have no bias and we have a low variability. So this is the best possible scenario here. This is what we want. All right. So we want to keep our variability low. We want to keep our bias low when we're taking our samples and doing our experiments. All right. So this just came in shorter than I thought it was going to be. So again, we have two other things here that I highly suggest checking out and playing around with. One of them is just a video. It's 3 minutes. It's cute. It's funny. It talks about the distribution, sampling distribution for bunnies and the sampling distribution for dragons, dragon wings, because of course we all know dragons are real. We've all seen Game of Thrones. I mean, it's history as far as I'm concerned. The other one, and I will post both the links at the end, is we take any distribution we want. We take a sample, it finds the mean, and we just keep doing this over and over again. Like we can click on it, so it'll do it 10,000 times or 100,000 times. In this distribution here, we can change the sample size here, like to n, like being closer to 25, I think is the biggest it'll go. And it becomes, you can see that it will become a normal distribution with the mean the same here as the mean up there. I didn't quite line them up there, but it will become a normal distribution. So you can see it and do it for yourself. We'll probably do it in class. All right, so that's it for 6.1. So there's no homework assignment with 6.1, so just go ahead and move right on to 6.2 or watch those other videos or play with that other sampling app.